So a sample of containing ammonium chloride was warmed with 100 cm³ of 1 mole per dm³ sodium hydroxide. After all the ammonia had been driven off, the excess sodium hydroxide required 50 cm³ of 0.25 mole per dm³ sulfuric acid for neutralization. What mass of ammonium chloride did the sample contain? Okay, so Ryan, can you tell me what's your answer for this before I start?
5.35 grams.
5.35 grams. Okay, can. Let me do it step by step. After all the ammonia had been driven off, okay, so basically what happened was ammonium salts, like not enough space. Let me try to squeeze. So ammonium salt is ammonium chloride, right? Reacts with a base, NaOH. So ammonium salt plus alkaline, it will give you ammonia plus salt plus water, correct? The salt will be sodium chloride plus water, H2O. So this is balanced. And then over here, we have 100 cm³ of 1 mole per dm³ sodium hydroxide. Then after all the ammonia has been driven off, excess, so this is total sodium hydroxide. So there is, some of it has reacted, but not all. So there is excess sodium hydroxide, which required 50 cm³ of 0.25 mole per dm³ of sulfuric acid for neutralization. So there's two equations that we are talking about here. Okay, the next one is an acid-base reaction. So we have a salt, sodium sulfate, plus water. Because acid plus base give you salt and water. So then if you balance it, this one times 2. And then there's 4 hydrogen. So oxygen, there's 6 in total. So 6 on the right also. Okay, good. There's 2 sodium on the left, 2 sodium on the right. Okay, so it's balanced. So it requires 50 cm³ of 0.25 mole per dm³ sulfuric acid. So they're asking you what mass of ammonium chloride did the sample contain. So when you read a question, this is what you can do on the sidelines. You can make notes, okay? So now, after making these notes, it's very clear. So we can start from where? It would be easier to start from the second equation. Why? Because the first equation, you only know the total amount of sodium hydroxide, and not all of it has reacted, right? So basically, you don't have the amount that has reacted. You can't do anything here using the first equation. So you can only use the second equation. So number of moles of H2SO4 first equals to 50 over 1000 times 0.25. So that would be 0.0125 mole. And then by mole ratio, 1:2, the number of moles of NaOH is 1:2. So therefore it will be 0.0125 to 0.025 moles. So that is 0.0. So I add on the piece of information, mole of NaOH. So what is this? This is excess, right? Excess NaOH that has not been reacted in the first equation. So therefore, to figure out how much actually reacted in the first equation, how much NaOH actually reacted in the first equation, we have to use the total minus the excess. Correct? Why do I want to do that? Why do I want to find the number of moles of NaOH that has reacted in the first equation? So that I can use mole ratio to find out the number of moles of ammonium chloride. Then from there, I can times MR to get the mass, right? So that is our strategy. Okay, if any of you have any question, please feel free to ask. Okay, so then next, let's find out the number of moles of total NaOH from the first equation. So that will be 100 over 1000 times 1. So that would be 0.1. Let me just check it on my calculator. Yep. Mole. So number of moles that have reacted. Number of moles of NaOH that have reacted equals to the total 0.1 mole minus away the excess 0.025 mole. So the amount that has reacted will be 0.075. Okay, so that would be, if I change color, 0.075 mole of NaOH reacted. Then by mole ratio, so number of moles of NH4Cl to number of moles of NaOH is 1:1. Let's just do a double check to make sure it's balanced. 4, 5, 5. Yes, everything's balanced. So it's 1:1. So therefore, if I have 0.075 moles of reacted NaOH, then I will have 0.075 moles of ammonium chloride that has reacted. So therefore, the mass of ammonium chloride will be number of moles times the MR. So N is 14 plus 4 plus 35.5. So that will be 4.0125 gram. So three significant figures will be 4.01 gram. Eh? Ryan, how do you get 5.35?
I forgot to minus the 0.025.
Oh, okay. Do you understand the part about minusing the 0.025?
Yeah.
Everyone understand this? This is a more complicated mole question. Okay, let me explain just a little bit more about this. So how should I say? Okay, because over here in the second sentence, right, they said excess sodium hydroxide. So the fact that they mentioned excess means that this total that they gave at the beginning, 100 cm³ of 1 mole per dm³, is the total, but not all of it has reacted. That's why there is excess. So you can only figure out, use the number of moles of NaOH that has reacted to do mole ratio. You cannot use number of moles of NaOH that has not reacted. Please take note of that, okay? I think, yeah, that should explain it. Anyone has any questions? So, Lincoln, you also made the same mistake, is it?
No, I forgot the times 2 here, like.
The mole ratio, is it?
The mole ratio.
Okay, so Lincoln made a mistake at the mole ratio side. Anyone else? So, Ryan and Decay. Decay and Raiden. How is it? Y'all get 4.01?
I got 4.68. I do not know how, but
No,
it's
I think you guys.
Oh, okay. So,
I left it
Raiden.
in 4 point. I left it exact. I didn't round off.
Oh, okay, wait. Raiden, Lincoln said that you made the same mistake as him. So you didn't do the mole ratio.
I didn't do the mole ratio.
Yeah, so that's your mistake. Then Decay, what do you say? Sorry, I didn't really get it. Can you say again?
I didn't put 4. I left it in like exact.
Oh, so you left it as 4.0125. Is that right?
I put the 2.5 behind.
Okay. That's you might be penalized -1 mark because in exam they want it rounded off to 368. Oh, but it's good that you managed to do it. Okay, very good. Then how come you tell me that your mole is weak? You're actually quite strong in mole, because judging from how you did in the MCQs also, seems like your mole is quite okay. Okay, then question 2. Question 2, Raiden, what's your answer?
Wait, my answer for question 2.
Yeah. Question 2A.
I got PbO2.
PbO2. Yes. Okay, that is correct. Okay, I realize I have a bit of an issue with space, but I think we can still figure it out.
Can you scroll back to the I fraction? Let me just the picture.
Here?
Yeah, thank you.
Okay. Then I'll pause first. Just let me know once you're done.
Yeah, thank you. I'm done.
Okay, welcome. So yeah, we have this. I'm trying to squeeze it into this bit. It should be doable. Okay, wait. On. I think it's better I do it below because I'm going to send this to you all, right? It's going to be very difficult to see because it's not organized. So empirical formula. This one is a bit unique for empirical formula. It's a bit different from the usual because you need to do your own calculations, okay? So this is how they determine the empirical formula of the oxide of lead. So they gave you the results. Mass of tube plus crucible is 25.45. Tube plus crucible plus content before heating, 37.92. And tube plus crucible plus content after heating is 36.24. So then, let us draw the table first, because if they want us to find empirical formula, you all know, right? We always have to draw this table. Divide it into 3 columns. So the first step will be to write down the mass first. And then what did they say it contained? It is oxide of lead. So there will be lead, Pb, and there will be oxygen because it's oxide. So what is the mass of lead? So before heating, what is inside? So mass of oxide of lead, let's figure it out. So the first step is mass. Sorry, yeah, I need to shift it down a bit. Okay, we need to do some calculations first. Mass of oxide of lead. Well, the oxide of lead will be the thing before heating, right? So it will be 37.92. Okay, minus away the mass of tube and the crucible. And you will get 12.47 grams. So this is the mass of the oxide of lead. Okay, you use tube plus crucible plus oxide of lead minus away tube plus crucible. Okay, so this one should be quite easy. Then next, what about mass of lead? So we have to break them down into Pb and O, right? That's how we have data to insert into our table. So how do we do that? The content after heating. What is the content after heating? Content after heating, if you take a look at this setup, this is the oxide of lead, and then they put in hydrogen gas. So what is happening? Y'all have learned metals. So y'all should recognize this setup. Okay? What happens? Let me ask Lincoln. Lincoln, what happens? What's happening? What is the product?
For the is it oxygen?
Oxygen. Oxygen. Not exactly.
I'm not so sure because we never test this.
Okay, Lincoln said that he's not so sure because his school never tests metals. Okay, so you will have lead. So the hydrogen will reduce the oxide of lead to lead. So what is remaining after the heating inside this setup will be lead. The oxygen you cannot capture, it's gone. Okay, so mass of lead will be, after heating, 36.24 grams minus away the mass of the tube plus crucible, 25.45. This will give you the mass of the lead remaining after the heating. Okay. So again, I'm going to repeat this. So you are heating it because we don't know what is the formula, okay? So we can only say that roughly this setup is a reduction setup. The hydrogen will reduce the oxide of lead. So oxide of lead will become lead, okay? Plus, of course, probably oxygen or water. So we don't really need to care about what is produced. Our main focus is what is inside here, okay? That's what you need to know in Mcqs. So after heating, the content after heating will be the PB. So tube plus crucible plus PB minus away the mass of tube plus crucible will give us the mass of the lead, right? So it will be 10.79 grams. And then mass of oxygen. So how do we get mass of oxygen? My oxide of lead is 12.47 grams. My lead is 10.79 grams. So the mass of the oxide part will be 1.68 grams. Okay, so then these are the numbers that I insert in. PB lead is 10.79, oxygen is 1.68. So this is the first step. Next will be to get number of moles. Mole, how do I get mole from mass? Mass divided by the MR, 207. So I will get 0.05. This is 1.68 divided by MR 16 equals to 0.1. Then next will be divide by the smallest number to get the ratio. The smaller number between the two will be 0.05. So then the last one is, you know, I never got the difference between row and column. I can never remember it. Okay, so this is a row, I guess. The last row is ratio. So it's 1:2. This one is rather straightforward. You do not have like 0.5 or stuff like that. So this one is quite straightforward. So therefore, it's PbO2. That is the empirical formula.
I got the empirical formula correct by the working inside, right?
How did you do the working?
Because I for the moles of lead, right, I use the grams for lead oxide.
Oh.
Yeah.
But do you get them? Oh, okay. For the mass of lead, you use the mass of lead oxide.
Yeah.
Okay. Now you understand?
Oh, yeah.
Okay, that's good. Yeah, I suppose you'll still get the right answer because you round off, correct? Okay, this is 2A. And then we still have 2B. So 2B is very interesting. Decay, what is your element? What is your element?
Oh,
Z?
this one I don't know. I didn't do it.
Okay. Ryan? Do you do this? 2B? Okay.
Wait, I'm not sure for this. I'm not sure how to do.
Okay. So seems like everyone's not very sure.
I did it.
Yeah, Lincoln, you did it right. What's your answer?
Tungsten. And I'm also sure.
Yes, good. It's tungsten. Okay, so let us take a look at it. When 0.997 gram of metal zinc reacts with fluorine gas, a mass of 1.203 gram of ZF2 is formed. Deduce the possible identity of element Z. So for this one, you have to first give the equation, okay? For most mole questions, right? The first thing you do is to write out the equation. So Z reacts with fluorine to give ZF2. So Z plus fluorine give you ZF2. Okay, then see what other information they gave us. The ZF2 is 1.203 gram. And they also gave us the mass of Z, 0.997 gram. Okay, so this one is a bit complicated. So from here, we are supposed to figure out what is that. So one thing that we know, the only thing that we know that would be in common is that the number of moles are the same because the mole ratio is 1:1, correct? So we have to make a chemical equation. Okay, we have to form a chemical equation. So your algebra skills come to play. So to get number of moles, I have to use mass divided by MR, correct? So mass of Z is 0.997 divided by MR. But the thing is, I don't know what's Z, so I don't know the MR. So let the MR of Z be X. So 0.997 over X will give you the number of moles of Z, correct? So this represents, let me write in another color, number of moles of Z. Okay. And then to get the number of moles of ZF2, it will also be mass 1.203 divided by MR. Okay, but it seems a little bit more difficult to do it this way. Sorry, let me make a little bit of change. Number of moles of Z equals to this moles, okay? So since number of moles of Z2, number of moles of ZF2 equals to 1:1, therefore, number of moles of ZF2 equals to 0.997 over X as well, correct? So therefore, that means that number of moles of ZF2, which is 0.997 over X, times the MR of ZF2, which is X plus 19 times 2, should be equals to 1.203 gram, right? So then next I have to just simplify this. 0.997 over X, then times X plus 38 equals to 1.203. So then for this kind, it's multiplication. So 0.997x plus 0.997 times 38 equals to 37.886 over X equals to 1.203 over 1. And then I cross multiply 1.203x equals to 0.997x plus 37.886. So if you're not good at math, it's hard to solve this question also. 1.203x minus 0.997x equals to 37.886. So that will be 0.206x equals to 37.886. So x will be equals to 183.9. And if you take a look at the periodic table, again, I only have the A level one, but it's still very similar. To check, we don't need to look, like they're very similar. So we look for 183.9 thereabouts. So you look, you see, tungsten is 183.8, right? So that is definitely the closest. The one before it, on the left and on the right, both are not as close as tungsten. So therefore, it is tungsten. So yeah, so therefore, Z is tungsten. So that's how you solve this question. So that's 2B. Understand? Any questions? Okay, no questions. Then we can go on to the last one. Sorry, the last one now, there's some issues with it that I corrected. Can I move on or you need more time to copy?
Can you give me a word to copy? Thank you.
Okay, sure.
Question about this. What is the mass before heating like more than after heating?
Sorry. Why is the mass before heating?
More than
Oh, because the oxygen is gone. Most likely it's a gas that is produced.
So if lead oxide, shouldn't it be the same? Citrus with lead.
But then after you reduce it with hydrogen, you are producing something else. Correct? So you will separate the lead from the oxygen. Wait, okay, let's wait for everyone to be done. Then I answer your question again.
Thank you, I am done.
Okay, Ken. Okay, so Lincoln has a question. So he is asking, how come the content after heating is lesser than the content before heating? It's because, right, the formula is, what was our empirical formula? PbO2. So it's PbO2 plus hydrogen will give you Pb plus H2O. Okay, so what will happen? It will give us Pb So actually, it really depends on, okay, PbO2 is rare. Usually in O levels, we deal only with PbO. This is common. So in this case, it will become Pb plus H2O. Okay, this is for the common one. But over here, we're not dealing with this. We're dealing with PbO2. Sorry, give me a second. There's a phone ringing. Okay. So for this, let's continue. Yeah, so for PbO2, like I said, it is very rare, okay? For O levels, it's actually out of the syllabus. But to explain this question, let me tell y'all how to do it. So it depends on how much is burnt. Let's see whether we can balance it first. The problem is that there's 2 O, right? So let me times this by 2. Oh yeah, I can still balance it. Let's check Pb, 2O, 2O, 4H, 4H. Yeah, this is balanced. So this is what happens. So before heating, you have PbO2. After heating, you have Pb and the H2O, because you're heating it, is strong heating some more. So the water will have left as steam. So it would have come out. So therefore, you have one portion that is gone. That's why the product is lighter, has lesser mass than the reactant. Understand? Yeah, okay. Okay, everyone. So then next will be question 3. Yeah, sorry for the issues with question 3, because the concentration is wrong. We have to correct it to 2.33. Okay, let's ask someone for their answer. I don't remember whose turn is it. I think maybe Decay. Can you tell us your answer for question 3? 3A part 1.
I kind of used the wrong concentration. I didn't see the message.
Oh, you didn't see the message. Okay. Okay, who saw the message and used the correct concentration? Ryan? Or Raiden?
Yeah, I didn't know how to do this question. I'm sorry.
Okay, that's... Now I have an issue identifying voices again. That was Ryan, right?
That was written.
Oh, no, it's Raiden, huh? Okay. Then what about Ryan? Okay, I think Ryan might be having some difficulty. Okay, let's just go through it. So a solution of dibasic acid containing ions X and Y of having concentration 2.33 gram per dm cube is titrated against sodium hydroxide solution of 0.2 mole per dm cube. So some things to notice over here, okay? It contains two ions, X and Y. It is a dibasic acid. Not sure whether all of you know what's a dibasic acid. Dibasic acid is like H2SO4, meaning in 1 mole of the acid, it will produce 2 moles of H plus ions. So it will dissociate to give you 2 moles of H plus ions. Okay, so 1 mole of the acid gives you 2 moles of H plus ions. That is dibasic acid. Okay. So it is titrated against sodium hydroxide solution. So we don't look at the calculations first because A part 1 don't need that. Then they told us in the last sentence, the products of the reaction is Na2X and water. Okay, which is expected because this is neutralization, acid plus salt, acid plus alkaline. So state the identity of Y. So you notice something, X is here. So X must be a cation or anion. Decay, can you answer this? Is X cation or anion? What about Raiden?
I don't know how to do this question.
Cannot hear. No, I'm asking you, just need to tell me from this formula, is X a cation or anion?
It's like and
Yes, it's an anion, correct. Okay, because you already have Na plus, which is a cation. So we bring that back to here. This is X is an anion. So Y must be the cation. And it's an acid. So in all acids, they will have the H plus, which is a cation. So therefore, ion Y is H plus. Understand? Okay, next. Hence, use this identity in A part 1 to construct a balanced chemical equation for the reaction. So this must form. So your anion will be X2 minus. Why is it X2 minus? Because Na is Na plus. So in order for them to swap and give you Na2X, so it means that the X must have a charge of 2 minus. That's how you can cross the numbers, okay, to get Na2X. So since X is X2 minus, so X2 minus and H plus, when you cross them, you'll get H2X. So this will be H2X plus NaOH. It will give you Na2X plus H2O because it's neutralization. So then we just balance this. 2 Na on the right, so 2 Na on the left also. And then there's 4 H on the left, so times 2 on the right. There's 2 O on the right, 2 O on the left, and 1 X on both sides. Okay, so this is balanced. Understand? Okay, then B. What is the concentration of this acid in mole per dm cube? So it has a concentration in gram per dm cube. So they're asking you, what is the concentration in mole per dm cube? Usually, it will be easy to get this because to go from gram per dm cube to mole per dm cube, you just have to divide by the MR. But over here, we don't know what this acid is. We don't know what's X. So we can't find the MR, so we can't do it that way. So then we have to rely on the information in this question. So let us write down the pieces of information that we are given so far. So this is 2.33 gram per dm cube. This is 0.2 mole per dm cube. You will need 15.2 cm cube of the acid to exactly react with 10.4 cm cube of sodium hydroxide solution. Okay, so they're asking for what's the concentration. What is the concentration of acid in mole per dm cube? So you can work from the mole ratio. You can work from the sodium hydroxide. Why? Because the values that they give you are exact, meaning they exactly react with each other, like they mentioned here. They react exactly. Okay, so we figure out the number of moles of NaOH. So that would be 10.4 over 1000 times 0.2. Volume times concentration will give you mole. So the answer for this is 0.00208 mole. Okay, and then so by mole ratio, number of moles of H2X equals to 0.00208 mole over 2, because the mole ratio is 1:2. So this will be 0.00104 mole. Okay. Since number of moles of H2X to number of moles of NaOH is 1:2. Actually, you should write this first, then this below. Okay, but doesn't matter as long as you understand. And then next, so since this is my mole, therefore concentration, okay, this square brackets represent concentration of H2X will be 0.00104 moles divided by the volume, because we know that the volume is 15.2 cm cubed. So divide by 1000. Because 15.2 is cm cubed, we have to change to dm cubed. So we divide it by 1000. So mole divided by volume give you concentration in mole per dm cube. So you will get an answer of 0.068421 mole per dm cube. So this will be your answer in mole per dm cube. Then next, so this is your answer for part B. Then C, part 1. Calculate the relative molecular mass of the acid. So this is for part B. Yeah? Calculate the relative molecular mass of the acid. Express your answer in whole number. So for C, part 1, 3C, part 1. Calculate the relative molecular mass of the acid. Oh, that would be easy. That's just one step. MR equals to the concentration in gram per dm cube, which is 2.33, divided by the concentration in mole per dm cube.
Miss Chow, Lia's in the waiting room.
Oh, okay, thank you. Eh? Oh. Thanks for informing, because sometimes I'm busy writing, I never see the notification. Okay, he's joining. Laye. Okay, I think he needs some time to turn on the audio. Laye, you finally managed to get back to your house?
Oh yeah.
How do you manage to get stuck outside?
Like I use my keys to unlock the door, and then I just put my keys back inside the house.
Oh, okay, no wonder. Okay, never mind. I'm glad that you are back in the house. We are doing the last question of the mole test. So the MR, so we are doing C part 1, okay? So the MR equals to 2.33. The MR equals 34.054. And express your answer in a whole number. Okay, so 34. And then C part 2. Hence, deduce the identity of the acid and the salt. So you see, it is H2X, right? So MR of X, AR of S, because it's an element, will be equals to 34 minus away 2, because there's 2 hydrogens, so that'll be 32. So let's go to the periodic table and figure out which one has 32. I close this. Okay, yeah. So the one that's closest to 32 will be sulfur. Okay, can see 32.1. So this will be the closest to 32. So therefore, it is sulfur. Therefore, X is sulfur. Therefore, acid is H2S and salt is Na2S. They asked us to identify acid and salt. So, yeah, that's that. Understand? Okay, if you all need time to write down, you can write down. I think later on, before I just take a photo for you all, I need to organize the answers first. If not, it looks very messy. Yeah. So let me know once you are done writing, okay, for those who need to write it down. Everyone done?
Yes, I am done.
Okay, yeah?
Yeah.
Yeah, done.
Yeah.
Okay. Okay, so we finished this. So for number 2, can I confirm with y'all that the thing that y'all don't really understand is the concept about metals that you are supposed to know? This equation, you're not sure what it was and what it became. Is that right? Okay, no response. I will assume so. Okay. So the next one today, we are doing the QA test. So I'm going to send the QA test to y'all now via WhatsApp, and then y'all can start doing. There are 11 questions in total, 9 MCQ and 2 structured. So yeah, I'm trying to see. I was quite surprised that last time, right, we couldn't finish it within the lesson. So then I'm trying to, reduce the number of questions so that we just nice can finish. Okay, y'all can start now. I'll send it to y'all now as well. Y'all can start looking at my screen first. Okay, I've already sent. Have y'all received? Can just give me a thumbs up in the Zoom if y'all have received, and then y'all can start now. And remember, it's supposed to be a test, so try not to refer because all of you have learned this chapter before. Okay? Okay, everyone, let's go through. Everyone is done with the MCQs. Okay, let's go through MCQs first. So, I think overall, on average, out of 9 questions, the average is 3 mistakes. So meaning the average is 6 out of 9, which is about 66%, 67%. So that would be a B3. Okay, but this QA, this topic is usually more difficult for everyone. So let's see. Number 1, a student tested a solution by adding aqueous sodium hydroxide. A precipitate was not seen because the reagent was added too quickly. What could not have been present in the solution? So Al3 plus, if you add in sodium hydroxide, you will form a white precipitate, which dissolves in excess. So is it possible for it to be Al3 plus? Yes, because it can dissolve in excess. So therefore, you might not see the precipitate when you add the sodium hydroxide too quickly. Okay, then Ca2 plus. For Ca2 plus, what will you get? You will get a white precipitate. Okay, I think everyone can see it now. Yeah, so for Ca2 plus, you form a white precipitate, but it does not dissolve in excess. So therefore, the answer is B, because it cannot dissolve in excess. So there's no chance of you not seeing a precipitate if you add too quickly. Okay, so answer is B, but let's go through the other options to confirm. So ammonium, when you add sodium hydroxide, what happens? You will get no precipitate, only ammonia produced, right? Pungent gas, which turns moist red litmus paper blue, is produced. So therefore, is there a chance that you do not see the precipitate? Yes. So therefore, it's not the answer. So then, lastly, Zn2 plus. Zn2 plus, if you add sodium hydroxide, sorry. For Zn2 plus, if you add sodium hydroxide, you will form a white precipitate, which dissolves in excess. Okay, y'all know a trick. If y'all think it's hard to remember, right? There's only 4, there's white, calcium plus Z. Z is the same as the amphoteric ones, right? Remember, zinc, aluminium, and lead. So over here, we're talking about ions. Huh? So remember that Z, all of them are white, okay? White PPT. But these 3, Z are the ones that dissolve in excess. Ca2 plus doesn't. Why do Z dissolve in excess? Because they are amphoteric, meaning that you see what is formed. Zn2 plus, you add sodium hydroxide, so you get OH minus. So then you will form ZnOH2, for example, correct? So this is your white precipitate. You have a precipitate because zinc hydroxide is not soluble. All hydroxides are insoluble except for group 1 and barium and strontium. Okay, so therefore zinc hydroxide is not soluble. That's why you have a precipitate and it's white color. Okay, so when you add in excess sodium hydroxide, what happens is it will form a complex ion compound, Na2ZnOH4. Okay, let's see whether we can balance this. You might have a bit too much H. Let's see, 2, 2, 4. Oh, there's 4 O's. Yes, balanced. 1 Zn, 1 Zn, 2 Na2. Okay, this is balanced. So this is the actual reaction. So this is a white precipitate, but when you add in excess sodium hydroxide, you will form this compound known as sodium zincate. Do you all learn this in school? No? Okay, but this why I'm talking about this is because it's quite important. Okay, I can't say it's that important. It's not so common, but sometimes they test. Okay, if you go to your textbook, you realize that there is mention of, if I'm not wrong, sodium aluminate. There is an equation that they give you. Okay, so if you go to the textbook, you can find it. So it is in the textbook. So this sodium zincate, it is soluble. So therefore, it will dissolve in excess to form colorless solution. Sorry, I've not enough space. So how come it can dissolve in excess? Because it is an amphoteric oxide. Amphoteric and only amphoteric oxides can react with bases. Make sense? Oh, okay. So what I was saying about this equation being present in the textbook is in acids and bases. You all can check it out. Okay, when you're learning about amphoteric oxide, there is this equation there. Maybe not for zinc, maybe for aluminium, but one of those. Okay. Yeah, so this is the reason why ZEP, all three amphoteric oxides, can dissolve in excess sodium hydroxide to form colorless solution. So very quickly, I'm just going to show you the equation for the other three. So AlOH3. So the white precipitate will be aluminum hydroxide. Y'all know that, right? Basically, when you add sodium hydroxide or aqueous ammonia, no matter which one you add, all the precipitates are hydroxides. Okay, so this is a white. Is it? Okay, I think I should shift it on top. I don't think this is a very good position to put it. Okay, so this is one, then two. Sorry, next time I need to take note of, like, you know, when I write, I need to take note of the sequence. If not, next time I think it's hard for you all to read also. So then plus, so this is the white precipitate that is formed when you add a few drops of NaOH. And then when you add excess NaOH, it will form sodium aluminate. If y'all think how to remember this compound is so difficult, right? So one tip is, what's the charge of Zn? Is +2. OH is -1. You have 4 of it, so it's -4. So therefore, you have ZnOH4, 2 minus. And then you have Na plus. So when you swap the charge, you have Na2, ZnOH4. Correct? Makes sense. So likewise, Al is +3. Okay? +3. You have 4 OH minus or -4. So overall, this will give you AlOH4 minus. So therefore, with the Na plus, you get NaAlOH4. So this is known as sodium aluminate. And the last one of ZEP is lead. So lead hydroxide. This is the white precipitate that you get upon adding a few drops of sodium hydroxide. Then after adding excess sodium hydroxide, you will get sodium plumbate. So how do you get it? This Pb, the charge is +2. 4 OH minus, so it's -4. So overall, you will have PbOH4, 2 minus. With Na plus, you swap to get Na2 PbOH4. So this is known as sodium plumbate. And then you need to balance the equation. Yeah. Okay. So y'all get the drift. Actually, you'll notice that there is a recurring pattern. It always bonds with 4 OH. Okay, so I think that makes it much easier to understand. Anyway, just wanted to do this because I know a lot of you are just memorizing it, right? But it can be quite hard if you don't understand. So I'm just giving you the understanding over here as to why this happens. Okay, number 2. An excess of aqueous lead to nitrate is added to aqueous barium chloride. The precipitate is removed by filtration. What are the main ions in the filtrate? So what will you get? lead-2 nitrate plus barium chloride, you will get lead-2 chloride plus barium nitrate. So which one is the precipitate? They said the precipitate is removed by filtration. So let's ask Lai Ye, which one is the precipitate? Lai Ye, you there?
So yeah.
Which one is the precipitate? Lead-2 chloride or barium nitrate?
Barium nitrate.
You sure?
Uh,
What is precipitate? Precipitate means that it is not
Stable.
soluble.
oh,
Yeah, so which one is not soluble between these two?
oh, lead to chloride.
Yes, because all nitrates are soluble, so it cannot be barium nitrate. All chlorides are soluble except for lead and silver, correct? So to do this chapter well, other than knowing the 4 tables, or some of you it's 3 tables, you also need to know the solubility table, okay? So, yep, this is removed. So what are the main ions in the filtrate? So in the filtrate, you'll have barium nitrate. So you have Ba2 plus, NO3 minus. However, don't forget something. There's one keyword here. An excess of aqueous lead-2 nitrate is added. So meaning that it is an excess. So meaning not all of it has reacted with barium chloride. There is still more left. So not all forms lead-2 chloride. So even though lead-2 chloride is removed, you will still have Pb2 plus and NO3 minus. But oh well, NO3 minus, anyway, they are the same, right? So what will you have? You will have Pa2 plus, Pb2 plus, and NO3 minus. So this one, I think, yeah, it's a bit tricky. You need to take note of the word excess. And then next, question 3. In experiment, 10 cm³ of 0.01 mole per dm cube copper 2 sulfate solution is mixed with 5 cm³ of 0.01 mole per dm cube sodium carbonate solution in a flask. Equation is shown below. What is in the flask when the reaction was completed? So for this one, right, I'm going to tell you something that's very useful, okay? So just now, Lincoln was asking me, how do you know what color are these copper compounds? That's very easy. You just need to know this few, okay? Firstly, copper metal. Decay, what color is copper metal?
Blue.
You sure? No, copper metal?
Oh, metal. Oh.
Yeah. The metal, the solid. You should have seen before, right? Copper is used to make some things like wire.
Like orange, red, that kind of thing.
Yeah, we call it reddish brown. Okay, to be honest, the funny thing is for O-level, you learn reddish brown. For A-level, you'll learn that it's pink. But anyway, you know like that shade lah, huh? And then next, copper 2 carbonate is a special one that you need to know. So this is a more difficult one. Okay, Raiden, can you tell us, do you know the color of copper 2 carbonate?
It is brown.
No, this one is very special. It is green. This is a very off one. Okay, it's out from the norm. So you have to remember copper 2 carbonate. Like, yeah, it is some one of these exceptions that you have to know. Number 3, copper sulfate or copper nitrate or copper chloride. All this, let's ask Ryan. Ryan, what color is this? Ryan, you there? Okay, maybe Ryan is facing some issues. Ryan, if you are there, you can just unmute, okay? If not, then maybe Lincoln, can you answer?
Oh, blue, right?
Yeah, so they exist normally as blue crystals or solution. Okay, so do you all notice something very peculiar? How do you know solid or crystal or solution? Because copper 2 carbonate is insoluble. All carbonates are insoluble except for spar and group 1. Okay, so copper 2 carbonate is insoluble, so that's why we never say solution. It's either solid or powder. Metal, you know, is the element, so it is just a solid or powder. Because if it's solid, you can make it into powder. And then copper sulfate, copper nitrate, copper chloride, these are soluble, so it's solution. And then the last one that you need to know is copper 2 hydroxide. You know, all hydroxides are all oxides and hydroxides. In case y'all don't know this, because this one not all schools teach, right? Y'all all learn sulfates, chlorides, nitrates, carbonates, but not all schools learn oxides and hydroxides. So I'm just writing it down. All oxides and hydroxides are insoluble, except group 1 plus barium or strontium oxides and hydroxide. So if you notice, of course, yeah, and ammonium. Okay, so ammonium plus your spar, right? So spar is made up of ammonium as well as sodium and potassium. Sodium and potassium are under group 1. Okay. This is the complete one, which is learned by most IP schools. Usually for O levels, you just need to know except for spar. That's enough. Okay. Some IP schools teach to here. This is the most complete one. Yeah. Okay. So copper 2 hydroxide. Oh, there's one more. Okay, copper 2 hydroxide first. This one is a let's go back to Layet. Layet, CuOH2. What color is it, and does it exist as a precipitate or solution or solid? I mean, solid is precipitate technically, so precipitate or solution. Layet, can you tell me the color?
The color of CuOH.
Yeah, CuOH2, the color, and is it a precipitate or a solution?
Is it like green?
No. Green is rare. Most copper compounds, right? If you really don't know anything to guess blue. Most of them are blue. Okay. Only copper 2 carbonate is green. Copper 2 hydroxide, but good guess. Okay, then can you tell me whether it's a precipitate or a solution? That one should be quite obvious because, you know, I just wrote here this thing.
It's a precipitate.
Yeah, correct. Blue precipitate. There's one last one that is quite annoying and you need to know also. So let's ask Decay. Decay, what color is copper 2 oxide, and is it a solid or is it a solution?
Can you repeat again?
Copper 2 oxide, what color is it, and is it a solid or is it a solution?
Is it black?
Yes. Wow, you know this. Okay, yes, you're very good. Yes, it's black. Is it solid or is it a solution?
Solution? I don't know.
No, you see, all oxides and hydroxide are insoluble except for group 1, barium, strontium, ammonium. So it is not the exception. So therefore, it is a solid. Understand? So this 5, just memorize this 5 in general. You will definitely be able to deal with all copper compounds. Okay? So I'm using the questions to teach some concepts because in school, usually your teachers don't teach this. Okay, usually your teachers just ask you to memorize. They don't really explain or summarize. Okay, So what is seen in the flask when the reaction is completed? Okay, so you notice something. Firstly, we ignore sodium because all sodium compounds are soluble, right? So it's a solution. And usually sodium compounds, they are colorless. Okay, so it's just colorless. Okay, we don't ignore it, but we just know that it's colorless. Then we have copper to carbonate, which we have learned here that is a green. It's a green solid, so it would be a precipitate if we are talking about in this context, right? When it's mixed with a solution, it'll be a precipitate. And then don't just look at the product. There must be a reason why they gave you all this, okay? Most of the time, they don't put it there just to trick you. So if you look carefully, you notice that the concentration is the same. So when the concentration is the same, you don't need to do calculations. This is 1:1, meaning 10 cm³ of copper 2 sulfate should react with 10 cm³ of sodium carbonate since they have the same concentration. But did that happen? No, there's only 5 cm³ of this. So this is a limiting reagent and copper 2 sulfate is in excess. This is the quick way to figure out which one is in excess and which one is the limiting reagent. Okay, it's a fast way. You don't have to calculate and get the number of moles. So then you have excess of this, meaning that you will still have CuSO4 in the solution. So CuSO4 is a blue solution. Correct? So the answer is B, a green precipitate, because you have copper 2 carbonate, and a blue solution, that's the excess copper 2 sulfate. Okay, so please take note of the mole as well. You also have to take that into account. Okay, next. Do y'all need some time to copy this? No reply. No reply is yes or no. Okay, I'll just go on. Anyway, I'll remember to send this to y'all after we finish this whole thing. So number 4, which of the following can be used to distinguish between aqueous zinc nitrate and calcium chloride? So number 1, sodium carbonate. So when they have this kind of questions, when this kind of question come out, you just have to just mix and match. Okay, so meaning if I use zinc nitrate, I will have zinc carbonate, and then plus zinc carbonate and sodium nitrate, right? If I swap just these two, just look at these two. So I swap their partners, so zinc with carbonate and sodium with nitrate. Okay, I'll have, okay, I know how to write it, like that. Okay, and then when I have calcium chloride, then I will swap partners and I'll get calcium carbonate plus sodium chloride. Usually, I don't care about the ones containing sodium because they are always soluble. All sodium salts are soluble. So they will not help us to distinguish. So then I look at the other one, zinc carbonate. Zinc carbonate is insoluble because all carbonates are insoluble except for spa, correct? And group 1. Okay, so the next one, calcium carbonate, also falls under that, so it's also insoluble. So can it help us to distinguish? No, it cannot. Okay, then the next one, I'm going to change color. Number 2, so zinc nitrate with lead to nitrate, so you will get zinc nitrate again, plus lead to nitrate again, because you have the same nitrate, so you'll get the same thing. Okay, and over here you'll get calcium nitrate plus lead to chloride. Okay, so both of these are soluble. This one contains nitrate, all nitrates are soluble. Then this The moment you see, actually, you should notice that it's insoluble. All chlorides are soluble except for lead and silver. So this is insoluble. So hence, can distinguish, right? Because you will have a precipitate, whereas the other one will not have any precipitate because they're all soluble. So it can distinguish. So 2 is correct. And then the last one, number 3, change color again. Zinc nitrate with sulfuric acid, you will get zinc sulfate. And like nitric acid. Okay, you don't have to care about the other one because acids are always soluble. So I'm just going to, care about the zinc sulfate. And then the next one will be calcium sulfate. And then, it will be hydrochloric acid. So I'm not going to care about it because it's, like I said, always soluble. So I compare this. Zinc sulfate. Okay, for sulfates, all sulfates are soluble except for, so I remember this by Singaporeans love barbecued chicken. Okay, so sulfates are all soluble except for lead, barium, calcium. Okay, so my own acronym is Singaporeans love barbecued chicken. So therefore, this doesn't fall under the lead, barium, calcium, so it's soluble. Then this one is insoluble, so hence it will distinguish. So the answer is 2 and 3, so it's C. Okay, next. Number 5. An aqueous solution of salt was placed in a test tube, and aqueous ammonia was gradually added from a burette. The mass of the precipitate was obtained when various volumes of aqueous ammonia were added, and a graph was obtained. Which salt would show this behavior? Okay, so what do you realize? This is the y-axis is mass of precipitate. So basically, this means that when I add in ammonia, as I add more and more ammonia, there'll be more and more precipitate until it just, stays constant. So what does this tell us? It tells us that there'll be precipitate formed, which does not dissolve in excess, right? Because if it dissolves in excess, then the precipitate will start to decrease, right? Whenever I add in excess, it will start to drop because it dissolved in excess, so there's no more precipitate. But in this case, it didn't. So the precipitate that is formed does not dissolve in excess. So this, I added aqueous ammonia. So what am I focusing on? The cations. Sodium is always soluble, so it will not even form a precipitate. So it's out. C is out. Copper to nitrate. So this one, what will happen? It will form a blue precipitate, correct? Blue precipitate, which is insoluble in excess. So possible because it does not dissolve in excess. But let's look at the others. Iron 2 sulfate. So iron 2 will form a, get wrong information. Because this is ammonia, insoluble in excess is for sodium hydroxide, which dissolves. So for copper 2, when you add in ammonia, it will form a blue precipitate when you add in a few drops, but when you add in excess, it will dissolve to form dark blue solution. So it's not the answer either. Iron 2 is green, so it will form a green precipitate which does not dissolve in excess, so which is insoluble in excess. And then zinc, it will form a white precipitate, which is soluble in excess. So it will dissolve also. So therefore, the only thing that will remain and does not dissolve is B. So B is the answer for number 5. Okay, next. Question 6. Question 6 is an interesting one because this is again those things that it contains those compounds that you need to know, but you don't learn it when you first learn it in school. So a yellow solid Q was formed when zinc nitrate was heated strongly with Bunsen burner while liberating a mixture of brown fume R. Whenever you see brown fume R for O levels, it's almost always nitrogen dioxide. Remember that. So this is the key. Brown fume is nitrogen dioxide. You don't learn it in the textbook, but for many questions, you need to know this piece of information. And a colorless gas that relights a glowing splint. Okay, so you know that this one they are referring to O2, oxygen. So the yellow solid turned white when it's cooled to room temperature. Okay, yellow solid turned white. This one you need to know is zinc oxide. Okay, zinc oxide will be yellow at high temperature. And white at low temperature. Okay, so this is something that is very interesting. Okay, you need to remember this. Yellow turned white is always zinc oxide. When you see yellow, right? Yellow, it can either be zinc oxide or it can also contain iodide. Because iodide will give you a yellow precipitate as well. Okay. So therefore, we have an answer. Our answer is B. Solid Q is zinc oxide. R is nitrogen dioxide. Okay. If you don't know the yellow turned white one, you can sort of make a guess. Okay. Because you have oxygen produced. So it is likely to be oxide. Because if it's hydroxide, you're likely to get water. Okay. But this piece of information, you also need to know it before you can use it. Okay, so answer is B. Question 7. Brass is an alloy made of copper and zinc. The identity of the metals in the alloy can be tested by dissolving it in dilute sulfuric acid followed by a series of tests. So, okay. Oh, okay. Yeah. So, number 1, okay, let's see what we are supposed to look out for first. Which evidences prove the presence of both copper and zinc? So meaning the observation must show you that both copper and zinc are present. So number 1, a blue solution is formed when alloy is dissolved in concentrated sulfuric acid. So concentrated sulfuric acid, well, these are metals. Okay, so metals will react with acids. So copper is unreactive. Normally it doesn't react with acid, but over here we have concentrated sulfuric acid. So it's strong enough to let copper react. So therefore copper and zinc will both react. So meaning that if they react, meaning that they will be used up, so they will dissolve. And then copper 2 sulfate, copper ion is blue. So yeah, we have a blue solution. Okay, and copper 2 sulfate, so we will form copper 2 sulfate, which is soluble, and zinc sulfate, which is also soluble. It is lead, barium, calcium that's not. So solution is correct. Blue color is because of the copper. Zinc is colorless. So therefore overall it's blue. So number 1 is correct. Number 2, a pale blue precipitate that partially dissolves is formed when excess aqueous sodium hydroxide is added. So let's see. When we add in excess aqueous sodium hydroxide, what will happen to copper? So copper will form copper hydroxide, which is a blue precipitate, pale blue if you want to be specific. Okay, and then what happens when we add a few drops? I'm talking about a few drops first. So zinc hydroxide is a white precipitate. Then later on, this is sodium hydroxide, so it is insoluble in excess. So it remains as a precipitate. And then zinc, because zinc is part of ZEP, so therefore it is soluble in excess. It will dissolve in excess. to form colorless solution. Okay, so you will have a pale blue precipitate initially, blue and white, so together pale blue. Okay, makes sense. That partially dissolves when it's in excess. So when at excess, the copper part remain insoluble, but the zinc part will dissolve in excess. That's why they say partially dissolve. So yes, it's correct. Okay, so number 2 is correct. Number 3, a pale blue precipitate that partially dissolves to form dark blue solution is formed when aqueous ammonia is added until excess. So when you add a few drops, then you will get CuOH2, ZnOH2. This one we mentioned, blue PPT, white PPT. And then in excess is dissolved in excess to form dark blue solution. And zinc hydroxide will dissolve in excess to form colorless solution. Ayo, my handwriting is getting very bad. Okay, wait. So is it correct? Blue, pale blue precipitate. This is correct. Partially dissolves to form dark blue solution. Well, it's not partially because both dissolve, so it should not be partially. So this is wrong. So the answer is 1 and 2. So it's A. Okay. Next. So you see, to do it, you really need to know all the tables very well. Number 8. An unknown colorless gas Y collected from a chemical reaction shows the following characteristic. It turns damp blue litmus paper red. So this tells you that it is acidic. So what can we cancel out from this? We can only cancel out carbon monoxide. Carbon monoxide is a neutral oxide. What are the neutral oxides? CO and OH2O. Okay. The rest are all acidic. Hydrogen chloride, nitrogen dioxide, sulfur dioxide, they are all acidic oxides. I mean C and D are acidic oxide. HCl, you know, like in water is acid. So next, does not put out both a glowing spleen and a burning spleen. This one, it doesn't really give us much hint. So the hint that is really given is this colorless. It has no color. Okay, so hydrogen chloride. Okay, nitrogen dioxide. This is another thing that you are not taught, but you have to know. It is a brown gas. Hey, did we say it just now? I can't remember.
Yeah, we said just now.
Oh, we said it just now. Okay, yeah. So nitrogen dioxide is a brown gas, so it's up. Hydrogen chloride, you will have white fumes, white gas. Okay, so it will not be completely colorless, so it's out. So it's D. Yeah. Okay, so that's how you get the answer. And of course, it does not put out a glowing spleen and burning spleen. So no hydrogen, right? And there's oxygen in it, I guess, because it does not pull out. Okay, so that's how you get your answer for 8. For 9, a student was given 2 separate test tubes containing aqueous sodium sulfate and aqueous zinc nitrate, respectively. Which reagents could be used to distinguish between the 2 colorless solutions? First, dilute hydrochloric acid. What will you get? So the first one, you will get sodium chloride. And sulfuric acid. But like I said, you can ignore the sulfuric acid most of the time. But let's just put it on. And then zinc nitrate, you will get zinc chloride plus nitric acid. Okay, so over here, the acids you can't distinguish because they are both soluble. Sodium chloride always soluble. Zinc chloride is also soluble. So cannot distinguish. So number 1 is out. Number 2, dilute sulfuric acid. So sodium sulfate, you again get sodium sulfate and sulfuric acid. Okay. So for zinc nitrate, you'll get zinc sulfate plus nitric acid. So this is also soluble. This is also soluble. So number 2 is out. Number 3, acidified lead-2 nitrate. So for zinc nitrate, you'll get lead-2 nitrate plus zinc nitrate. Again, the same thing. Oh, that's zinc nitrate. Sorry. So I need to shift this over. Okay. This is not so easy. Seems easier for me to just cancel and rewrite. So zinc nitrate plus lead-2 nitrate. And for sodium sulfate, you'll get lead-2 chloride. Lead-2 sulfate, sorry. Plus sodium nitrate. Sodium nitrate, you know that sodium is always soluble, nitrate also. Okay, so this is soluble. And lead-2 sulfate. All sulfates are soluble except for calcium, barium, lead. So it's there. So it's insoluble. So then zinc nitrate is always soluble. All nitrates are soluble. So there's one will be insoluble, one will be soluble. So the insoluble one will get a precipitate. The soluble one will be a solution, no precipitate. So yes, it can distinguish. And then the last one, aqueous ammonia. Okay, I'm going to try to shift all this up. Yay. Okay, I'm going to shift this up as well. Okay, I add aqueous ammonia. So this is a distinguishing test for sodium, but you know you get sodium hydroxide, which is just colorless, right? Soluble, okay? And then zinc, well, you will get white precipitate. Oh, sorry, indirect zinc hydroxide first. White precipitate, so insoluble. This is colorless solution. So immediately you have a contrast ready. You don't even need to talk about excess or not. So 3 and 4, so the answer is D. Okay. Okay, so I think the only one that I never checked yet is Lincoln. Lincoln, how many marks do you get? 6 marks. Okay, so that's the average also. So most of you got 3 mistakes. That's the average. Okay. There's and then one got 2 mistakes. Another one got 2 correct. Okay. So that's the stats for this. So now we unfortunately don't have enough time to finish again. What can I do? Maybe next time I need to give lesser questions. Okay. But oh well, I think it's good practice because I think all the MCQs here are quite different. Okay. So you can finish 10 and 11 on your own. And then next week we'll start with going through this. Okay. If there's any other topics that you are not very sure, just let me know via message. Okay. Bye-bye, everyone. Thank you.